So here we're gonna talk about what a solid or revolution is. We're gonna introduce the idea and the formula here for finding the volume of some object. Now, what we're creating here, guys, are things that are three-dimensional objects that are symmetrical. Okay? And they're symmetrical because what we're doing here is we're taking some kind of an area. Like here you see the integral from a to b of f of x, that green area there. And then we take this area and we kind of make it into three dimensions by revolving it around the x-axis. Okay? We revolve it around the x-axis, and I want to actually start with something you guys know, and that is a cylinder. Okay? Now a cylinder has a volume of the area of the base times the height. Okay? Now if I were going to create a cylinder by this method, a cylinder is the same radius the whole way of its height, right? So that means my function would be a constant. Okay? So here is f of x. Okay? And f of x just equals some constant. So we'll call it constant c. And then if I'm going to make a cylinder out of this, I'm going to define two values, a and b. Okay? And notice here, what I end up having is a rectangle, right?
Yeah.
Okay? Now, what is the area of this rectangle? Base times height, right? What's the length of the base here? B minus A, okay? So the base of the rectangle is B minus A. What is the height of the rectangle?
C.
That's C, okay? So the area of the rectangle is C times B minus A. Now what's another way I could express the area of that rectangle? As an integral, okay? Or I would have the integral from a to b of that constant function. Okay? Now, let's step away from the integral for a moment and let's look at this more geometrically. Okay? Let's say I took this rectangle and I revolved it around the x-axis. Okay? So I have this cylinder. Okay? You see that? It's a decent 3D drawing. And then this edge of the cylinder would be the part of the function. Okay? Now, we know that the volume of the cylinder is the area of the base times the height. Okay? So the area of the base. The area of the base is going to be pi r squared, right? Because it's a circle. So the radius here equals c, right? So pi r squared h. We have here pi times c squared. And then what's the height of this cylinder going to be?
The height is B minus A.
Yeah, this is our height here. That's the b minus a. Are you seeing some similarities here?
Yes.
Okay? So our volume, you notice what we end up doing. We end up taking this function, this radius, and we square it. So it's pi r squared. And then we multiply it by the b minus a. Okay? Let me rewrite this a little bit. We had that c was f of x. So our volume is pi times f of x squared times b minus a. Okay?
So it was a rectangle and now it's a cylinder. So we're using the, what we know about the rectangle.
We took the rectangle and we revolve it around the whole thing. Around the x-axis. And that's what makes it into a cylinder. Okay? You think of it like that rectangle is kind of like the cross section this way, and we just revolve it around, and it's going to make it a cylinder. Okay? Now, we already said it's the area. Okay, the area was the integral. Well, if we look at this, our volume we can also now express as an integral. Okay, the volume is going to equal the integral from a to b times pi. It's pi times the integral from a to b of f of x squared dx. And notice the entire function gets squared. Okay? Now you might say, well, where'd the b minus a go and where'd this dx come from? Well, remember that differential, the dx was the width of all those rectangles? Well, here you put all those together and that's what gives you the height of our cylinder. Okay?
dx is equal to b minus a.
So what we're doing here is this pi r squared, or pi times the function squared, gives us the area of this circle. And when we do the integral from a to b, just like we did those Riemann sums with the rectangles, you add up all the little rectangles. Here, we're adding up all these tiny little circles, or discs you could call them. And when we do the integral from a to b, it adds all of them up and makes a cylinder that goes all the way from a to b. Okay? So that's what we're doing here. And here's our kind of simplified formula for this, because we could do this with more than just cylinders. We can do this with any shape we want. Okay? We're going to do a volume of revolution around the x-axis is pi times the integral from a to b of the function squared dx. Okay? And the cool thing about it is you can see here we have this f of x, and they even showed the bottom as we revolve it around here. Okay? We're revolving this around the x-axis, and you can see that kind of cool shape that we'd end up with. Okay? But guys, this is, as we're designing things, if we want to design something in a particular shape that will hold a certain amount, we can design it as a solid of revolution. Okay? Think about the fuselage on an airplane. Okay? The fuselage on an airplane, you have kind of this this end that's kind of flat, all right, and then you have, it kind of looks like this, right?
What's a fuselage?
The thing that holds fuel. Okay? Let's say we wanted to make something that held fuel for an airplane, okay?
I thought you were saying fuselage.
Fuselage. Yeah. But here's the thing, if we have this, if we can figure out whatever function this is, if we can model that, then we can figure out, okay, if I revolve that around the x-axis and make it nice and symmetrical so it has good aerodynamics, how much gasoline will that, or how much fuel will that hold? Okay? And if it doesn't hold enough, then we need to rework the design. Okay? Maybe we need to make it a little bigger like this. Or maybe we need to make it longer. Okay? But we can then manipulate our function to, and also know exactly how much fuel this thing will hold in the end. Okay? And really, guys, any kind of a container, if you want it to hold a certain amount, you could do that. Okay? In fact, there was an IA I moderated last year where a student was decided he wanted to design a lava lamp for his brother, and his brother really likes bowling. So he decided that he would make his lava lamp in the shape of a bowling pin. So he had this, okay? And what he did is he created a piecewise function and then revolved each piece of it around the x-axis and was able to add up all the volumes, and he figured out how much liquid he would need to make the lava lamp with. How much liquid he would need to fill it up with. So, any kind of a container, you can use this type of a thing. If you're going to make it symmetrical, you can use this type of a thing to figure out what the volume would equal. Okay? Let's do one that we could do using geometry. You guys know how to find the volume of a cone. It's 1/3 pi r cubed. Or I'm sorry, 1/3 pi r squared h. Here we have part of a cone, so we'd have to find the whole thing and then chop off the tip. Okay? But we can do this instead. We have the line y equals x over the interval from x equals 1 to 4. And we're going to revolve this 2 pi radians around the x-axis. So we're revolving it a full 360 degrees. Okay? So the way we'd set this up is we have our volume is going to equal pi times the integral from 1 to 4 of our function x squared dx. Okay? So we're doing our function, we're squaring it. So we get pi times x cubed over 3 evaluated from 1 to 4. Okay? So don't lose your pi along the way, but we have 64 thirds minus 1/3, which is 63 thirds, which happens to be 21. So this is 21 pi cubic units, because it's volume. Okay? And that's all there is to it. It's actually a pretty simple formula to use. Okay?
Okay.
Here's another one that's a little more complicated. This one looks pretty cool if you sketch it. We have the y equals x squared from 0 to 5. So here's 5. 0 to 5, it's going to look like this because it's going up to 25. Okay? Check out what this looks like. It would be, we'd have this, and that would be like this enormous circular part. Okay? Kind of like this flared. See that? Kind of a big old horn of a bell or something like that, or bell of a horn, horn of a bell, bell of a horn or something like that. Okay? That's kind of a cool looking thing though. But what volume would that be? Well, we do the integral from 0 to 5 of x squared squared dx times pi. Okay, so there's our volume. So pi, we have x squared squared, which is x to the 4th, so the integral is x to the 5th over 5. If we're evaluating that from 0 to 5, when I plug in 5, I end up with 625, because 5 to the 5th over 5 is 5 to the 4th, and that's 25 squared, which is 625, minus 0. So this whole thing is 625 pi cubic units. Okay?
Should we we should always leave it in terms of pi.
Yeah, don't bother, you know, plugging in pi, just leave your answer in terms of pi.